Hi, we're on Chapter 3, Applications of Derivatives. We're on the first 2 pages of Chapter 3 with the mean value theorem and Rolle's theorem being section 3.2 in your textbook. So what we're going to first discuss is tying the graphical interpretation to the formula. And according to the mean value theorem, we have that the slope of the tangent line, which you see in green, so this is my tangent line, of a function is equal to the slope of the secant line. And the secant line is a line that passes through any 2 points on the graph. Given that, a very important given that the function is continuous on a closed interval, meaning that it must be continuous even at the endpoints, so there should be no holes at f of a and f of b, otherwise we can't apply the mean value theorem, as well as differentiable, which means that you can take a derivative on the open interval between a and b. And that's important to note because that means we can't apply MVT for things like absolute value functions and anything that where you have a corner or a cusp or a vertical tangent. And according to the mean value theorem, we are guaranteed a value c, which is an x value, somewhere between a and b, such that the slope at a point, which is the slope of my tangent line, also known as the derivative at that point, is equal to the slope of the secant line, f of b minus f of a all over b minus a. So to color code everything, this representation of the slope of the tangent line is in green, to go with the green curve, and then the slope of the secant line is given below. And if you recall, slope of the secant line is simply change in y over change in x, and also known as average rate of change, or AROC. And the slope at a tangent line is the derivative. So here we go. We'll take a look at the first example. On the first example, they asked us to find a value c satisfying the conclusion of the MVT given f of x equals radical x on the interval from 4 to 9. So with the requirement of continuity, we're going to make sure that the function we're given, f of x equals square root of x, from what we recall from pre-calc honors, is continuous from 4 to 9. So it will exist a value c such that the MVT can be applied. So let's start with the slope of our secant line being in burgundy, and then the slope of the tangent line being in green. And graphically speaking, the interval is 4 to 9, which is a is my 4 and 9 is my b. So that's an interval that's given there. And what we're going to do is find the slope of the secant line, which should be the line that connects these 2 points. Best secant line right there. Okay, and we're trying to find some value between a and b such that the tangent line is going to be equal to that line. So let's see if that exists. We're going to start with finding the slope of the secant line on the right, being f of 9 minus f of 4. Again, I'm getting the 9 and the 4 from that interval, all over 9 minus 4. And over on the left-hand side, I'm finding the slope of the tangent line, which I know is the derivative of square root of x. Okay, if we want, we can convert f of x to be f of c equals square root of c, since they're referring to this x value as c, and then take the derivative accordingly, knowing that square root of c is c to the 1/2. So 1/2 c to the negative 1/2. And we go on to solve the right side to get f of 9 is square root of 9 minus square root of 4 all over 5. Square root of 9 is 3, square root of 4 is 2, so we get 1/5 equals 1 over 2 square root of c. And now solving this equation, just going to keep this color. We're going to cross multiply, get 5 equals 2 radical c. Divide both sides by 2 and get, let's continue up here, 5 halves equals radical c. if I square both sides to undo the square root, I end up with c equals 25/4. And which when we simplify this, is 6 and 1/4. And we always want to be cautious of whether or not this value actually does fall in between A and B, which is 4 and 9. So if I find that on, let's go ahead and find that on my graph. 6 and 1/4 is about right here. And so the slope of the tangent line at that point is equal to the slope of the secant line. And so 6 and 1/4 being between A and B means that that is the solution. If you find a C value and it's outside that range, then we say that that value doesn't exist. All right, on example 2, find the point C on the interval from 1 to 3 where the slope of the tangent line equals the slope of the secant line on the graph of f of x equals x cubed. I'm going to have you guys pause and try to set up the derivative being equal to the slope of the secant line, and then double check your work. All right, so f prime of x, we're going to find f prime of x. We're going to set it equal to the slope of the secant line. Actually, let me call it c so that we keep it consistent. So this is f of c equals c cubed. And so if I do the slope of the tangent line is equal to the slope of the secant line, I have the slope of the tangent line. Don't forget to take derivatives, because I notice that's one thing that students will do is maybe perhaps make the switch over to c, but then forget to take the derivative. So slope of the tangent line is 3c squared. Power rule is equal to 3 cubed. I'm going to go ahead and plug my a and b in. So f of 3 would be 3 cubed. F of 1 would be minus 1 cubed, all over 3 minus 1. 27 minus 1 is 26 over 2. Is equal to 3c squared. If I simplify further, I get 3c squared equals 13, or c squared equals 13 over 3. Anytime you guys are solving by square root method, we want to keep in mind that we have two possible answers, plus or minus rad 13 over rad 3, which if we rationalize that by multiplying by rad 3 over rad 3, we get plus or minus radical 39 all over 3. And the question is, are both of those in my answers? So radical 39 is some number between 6 and 7. And if I divide that by 3, I do get that the positive value is in the interval from, remember answers must be between 1 and 3. So don't say that both are the solutions unless you've gone back and checked to see if they are in the interval. In this case, the negative one does not fall in that interval, so my only solution should be radical 39 over 3. On example 3, you're given a table of values that represents s of t. Our position of our particle is s of t, and we're given that it's differentiable everywhere. So below that, if you guys can make a note that differentiability means that it implies continuity. A function must be continuous if it is differentiable. So that's important for us to then make certain assumptions. So part A, is the particle ever exactly 7 inches? If it's continuous, if I look at my y values, which represents the position particle in inches, we see that there is a spot sometime between time t equals 3 and 4 seconds that it goes from 6 to 9. So being 7 being between those two values, we're guaranteed that it will pass through 7 as a position. So how do we know that? You might recall a theorem. At this point, if you can type in the theorem and let me know, or select from the theorems that you see in multiple choice there. Good if you guys picked intermediate value theorem. Okay, so how do we state the intermediate value theorem? We say, since s of t is continuous, between time 3, or let's just say between 3 seconds and 4 seconds. Since S of t is between 6 and 9, we are guaranteed a value of 7 on this interval. By intermediate value theorem. So note that I stated continuous, I stated intermediate value theorem, I stated the range of the y values as well as the x values over which it occurs. On part B, is the particle ever traveling at a velocity of 3 inches per second? So I accidentally deleted this, so let me write that back. But we're looking for inches per second is a rate of change. So we're looking at S of t over t, and it's asking for exactly 3 seconds, 3 inches per second, which is an instantaneous velocity. So we're looking through our table of values for when the change in position over the change of time is equal to 3 inches per second. And if I search and do the slope in my mind, change in y over change in x, I see that between the same time, there exists the slope of the secant line being equal to 3 as well. So yes, by MVT, between 3 seconds and 4 seconds, the slope of the secant line is equal to 3 seconds, 3 inches per second, which means there is a value C between 3 and 4 seconds, such that the derivative of S of t is equal to 3.